Everyone. So this is the last thing that we're going to talk about with waves, in particular, some of the phenomena that are unique to waves. This is going to be split into four different parts. For the most part, everything that we're going to talk about in this topic are just very quick things that you'll need to know. So a lot of this, you already started learning some of this stuff in the POGL, but some unique characteristics that we're going to talk about with waves are things like reflection, diffraction, refraction, polarization, and Doppler shifting. These are most of these are properties that waves will exhibit uniquely. So for the most part, reflection, diffraction, polarization, and Doppler shifting are all things that you just kind of need to recognize that they're occurring and what it looks like. Refraction is the only one that actually deals with some sort of calculation. So we're actually going to talk about the three of them today. Now, before I continue, I just want to mention this in case you see a question about it. The concept of wave theory and particle theory. Basically, the idea is in physics, things are split into two categories: waves or particles. So, for example, a tennis ball is a particle. Uh, Now, wave theory basically describes the behavior of waves, and particle theory describes the behavior of particles. There are certain phenomena that only really occur with waves, and there are only phenomena that really only occur with particles. Like you can't describe some things that are particle nature by using the concept of a wave. And that's what this is all about. So this is just something that you need to know. Just the idea that something like diffraction, polarization, Doppler shifting, interference, they're all wave in nature. Uh, these are things that only waves can do. For example, interference. We mentioned this before, that interference is when two waves occupy the same space at the same time and they'll combine their amplitudes together. So they basically merge. This is something that cannot be described through particles because two tennis balls, for example, it's impossible for them to occupy the same space at the same time. They'll never merge into a bigger tennis ball. So interference does not occur with particles. It can only occur with waves. So the particle is just like what are things that particles can do that we can describe using the concept of like a tennis ball. That's usually what I think about. The main thing that is described through particle theory is momentum. So momentum, something that can only be described when we consider something as a particle, not as a wave. Really, what this boils down to is you recognizing that something like reflection is unique because it's one of the few phenomena that actually uh, satisfies both theories. Like waves will reflect. You send a wave to a wall, it reflects back. Same thing with particle. You take a tennis ball, you throw it at a wall, it's going to bounce back. So reflection is something that it can actually be described through both of these models. Refraction, depending on who you talk to, could also be described using wave or particle theory. I kind of tend to think that it can be described through both, but that really depends on the person. So, like I said, it's just something that you need to recognize. Now, there's this thing called a medium change. So, I had mentioned the term boundary just now, but a boundary is what we describe as when the medium is changing. So, medium, as you know, is the material that the wave is moving through. So, like if you have a water wave, the water the wave is traveling through the water. If that water changes, maybe it goes from being all salt water to fresh water, or maybe it goes from a deep pit of water to a shallow bit of water. That would be considered medium change. So wherever that difference in that change occurs, that's what we would call the boundary. So perfect examples would be things like glass and water. So light is traveling through air. All of a sudden, it comes across this glass. It's going to travel differently in the glass. So that glass is considered a boundary. Now, every time a wave comes towards the boundary, when there's a medium change, um, there are three things that are going to occur. Some of the wave is going to transfer and move through the medium. Some of it's going to reflect off of that medium and bounce back, and some of it's going to be absorbed. This is the main reason why when someone's looking through a windshield, not only can a person inside the car see what's going on outside, but a person standing outside the car could also see their own reflection, just like in this picture. This uh, occurs here too. We can see the light passing through the water from the rope inside here, but we can also see the light being reflected off of the water surface. So some of the light gets transferred and moves through, some of it gets reflected, and some of it gets absorbed. I have this little animation right here that kind of shows that same idea. So we have a wave traveling through one string. Part of the wave travels through the heavier string, but part of it also gets reflected. And same thing over here, part transferred, and then part of it also gets reflected. All right. So again, something that you just kind of need to recognize that these three things are always occurring. Now a little bit more on reflection. So you should have learned this in the POGIL. We have two different rays, incident ray and reflected ray. Incident is what's coming in, incident, incoming, um, and reflected ray is what's bouncing off. We have angles called the incident and the reflected angle. The important thing is that these two angles are always to the dotted normal line. They pretty much will always give you the dotted line, but they may not always give you these angles. So just pay attention. If they explicitly say angle of incident or angle reflection, they're talking about these angles. There are some times where they may give you these angles, but they'll go through a little bit more lengths to kind of explain what those are, like the angle between the incident and the mirror or something. So if you see the phrase angle of incidence or incidence angle, that's this line to the normal. You want to make sure that these angles are always to the normal. Now I know what some people are saying, thinking, well, if these angles are the same, well, wouldn't that make sense that these angles are the same? So does it really matter? The answer is yes. First, if we had a curved or an irregular shaped mirror, then it's easier to actually measure to the normal than it is to the surface. But when we get to refraction, it's going to be super important that you always take the angle to the normal, because if you don't, you're going to get your answer wrong. So just make sure that the angle is always next to the dotted line. There are two types of reflections. Regular reflection is what we typically think of with a mirror, where light comes in and then bounces off because off of the flat surface. They come in and bounce off at all equal angles, and this is what's going to produce an image. So this is regular reflection. Diffuse reflection is what's occurring on every other surface. So when you have a rough surface, you have all these little bumps and grooves. As the light comes in, it's going to bounce off at all completely different angles because of the different shape of the surface, and this is going to produce no real image. So this is what's occurring when you're like looking at a somewhat smooth surface and you can sort of see an outline of your body, but not really anything in particular. That's diffuse reflection. Like you're seeing a little bit of something because it's a slightly smooth surface, but it's not crystal clear like with the mirror. Now the next thing that you need to recognize is this phenomenon called diffraction. So diffraction is the spreading of a wave through an opening or around a boundary. So here we have these two openings. The wave's going to come through, and instead of just going straight on like this, with the area behind here being a shadow area, what is going to happen is it's going to slowly creep around and across here. So eventually it will actually spread around these two boundaries. Now the amount that it spreads is dependent on the wavelength and this opening size. I'll show you a few examples in a second. But one thing to note is that the wavelength always stays the same. So if this is 10 centimeters, then this is also 10 centimeters. So the wavelength doesn't change. It's just that it gets bent. It goes from being flat lines to curved lines. Now, if the wavelength is bigger than the spacing, it's going to spread out a lot. So bigger the wavelength, bigger the spread. When the wavelength's smaller, it doesn't spread as much. So smaller the wave, smaller the spread. So it's going to take a while for it to finally get around here. So just something that you need to recognize. Again, these are just one-off questions. You'll see it, recognize what diffraction looks like, and then maybe see a question about which one's going to diffract more or less, and that's all about the wavelength. If the wavelength is bigger and like much bigger than the spacing, then it's going to diffract more. There's something called diffraction pattern. This is actually how we're able to recognize that something is exhibiting wave properties. Basically, we send something through these two openings, and we get these the waves kind of diffracting outward like this. Again, you get this cone shape coming from the openings, and this kind of goes with what I talked about with interference. So as it goes through these two openings, we get two cones, and where the cones interact, we get a screen on this side that shows areas of constructive interference with the bright bands and destructive interference with the dark bands. Um, Basically, a good example of this is you take light, you shine it through these two openings, and you have a sensor here that is recognizing light. So this is where we would see light, and then these dark areas we wouldn't see it. This is just another example of it. In fact, if you look at this and you kind of squint your eyes, you can actually see, little bands in here, and that's caused by constructive and destructive interference. All right, so anytime you see the phrase interference pattern, it's referring to this with these bright and dark bands on a screen, and they show um, they're showing wave properties. Okay, the last thing I want to talk about is this concept of polarization. So polarization is something that only affects transverse waves. And it's mainly used for light, though it works for any transverse wave. Now, the reason why it works for light, mainly for light, is because light is actually what's called a double transverse wave. It has a vertical transverse component, but it also has a horizontal component. So it looks something like this. This is actually caused by the electric field and the magnetic field, hence why it's called a electromagnetic wave, because it's composed of electric and magnetic fields. But yeah, it has these two components. So again, you just need to recognize that polarization occurs, when it occurs, and what it kind of looks like. So polarization is the concept that part of that transverse wave is being canceled out. So it's a filter essentially. That's actually the best way to think about it. If you want, you can write that in that it's a filter. So here we have light coming from a flashlight. It has a vertical and horizontal component. If we send it through two vertical filters or two vertical polarizers, basically what that does is it filters out everything but the vertical side. So this horizontal component gets crossed out and it just looks fine. Best way of thinking about it is similar to sending a wave on a string, and you have like a picket fence with these vertical slots here. It's only going to allow for a vertical wave to pass through because of the vertical openings. On the flip side, if we take a vertical polarizer and we combine it with a horizontal polarizer, these two are going to block out vertical and horizontal waves, leaving us with nothing. Same thing with here. If we send a wave through a vertical picket fence and then we have a horizontal fence next to it, the horizontal parts will actually block out this vertical component and we get left with nothing. So again, polarization is just a filter. So here's a question I want you to think about. Pause video, work on yourself, and we'll go over in a second. So can sound be polarized? Answer is no, because what type of wave is sound? Longitudinal. It is not a transverse wave. So only light, mainly light, can be polarized. Sound cannot be polarized. All right, here's another question. You can pause the video, work on yourself, and we'll go over in a second. All right, so here we have two waves. We have a solid line, which is vertical, horizontal, dotted, which is horizontal, goes through this box, and only the solid vertical line remains. This is a filter, which is also called a polarizer. Who would have guessed that the question on polarization would be a polarizer? All right, and that's pretty much it. We'll finish talking about some of the other phenomena. If you have any questions, please let me know, and I'll see you later.